Alright everyone, today this video is going to be about the kinetic molecular theory, or KMT. All the vocabulary for this section is already uploaded. It's already on Classroom, it's in Quizlet, so make sure you get started on that. Same as always, 3 activities for each set. I think there are 2 just one. No, there's only one for this section. So just make sure you get those 3 activities done. Alright, so let's get started with kinetic molecular theory, or KMT. What the kinetic molecular theory tries to explain is why matter behaves the way it does. Talking about atoms and molecules, and if we can understand their behavior, then we can understand why larger things will behave the way that they do. So let's start with a couple of definitions. So kinetic refers to motion. It's a physics word that we use a little bit in chemistry. So whenever we talk about kinetic, we're talking about motion, about movement. The formula that you'll learn in physics is, let's go into this. So kinetic energy is the energy of motion, right? It's the energy of kinetics. And as I was saying, the formula that's used in physics for kinetic energy is mass, the mass of the object, times the velocity of the object squared. And then you take half of that, and that's going to be your kinetic energy. Well, I'm not really too concerned that you know what the formula is, as long as you remember that 2 things impact the kinetic energy of an object, of an atom, of a particle, whatever it is we're talking about. 2 things affect the kinetic energy. We're talking about the mass of whatever it is we're talking about, right? The mass of your object, and the velocity, the speed of your object, okay? Change one of those 2 things and we change the kinetic energy. This theory was first published by Rudolf Clausius in 1857, so it's been a while, and understanding this theory has helped us understand, again, how and why matter behaves the way it does. You'll also see this theory sometimes called the theory of moving molecules, which makes sense since kinetic means motion and molecules, blah, blah, blah. Okay, so we're talking about the motion of molecules, the motion of atoms. If we're looking at particles in solids, okay, solids, like all matter, is made up of a bunch of particles, atoms or molecules, depending on what solid we're talking about. And they're packed very tightly together, right? You learned this in 8th grade. They're packed very tightly together. So would we expect them to have high kinetic energy or low kinetic energy? Remember, kinetic energy is the energy of motion. And if things are packed close together, how much motion do we think they're going to have? Do they have a lot of room to move around? Think if you're the atom in the middle and you've got atoms all around you, are you going to be able to move very much? Well, of course not, which is why we say that solids are going to have low kinetic energy. They still have some, right? If we still have atoms and molecules here, they're not able to move around like this. It's more of a vibration, and that's what we're talking about. These atoms and molecules are in a solid, most of their motion is going to be vibration, but they're still moving. They still have some kinetic energy. If we move on to look at liquids, liquids are still made up of atoms or molecules, depending on which liquid we're talking about. They're still held by their neighbors, right? They're still locked in, but they have more freedom to move around, more room to move. And so that more room, is that going to lead to more or less kinetic energy? Well, of course, it's going to lead to more kinetic energy. They're able to move more, they have more energy, they're moving faster, and so they're going to have more kinetic energy in a liquid than in a solid. And if we keep moving and we go into gases, gases obviously very few particles in a large amount of space, so they have tons of room to move around. Tons of room to move around means they're going to move a lot. A lot of kinetic energy. Gases have way more kinetic energy than liquids, and especially way more than solids. Liquids have a little bit more than solids, but gases have way more than either one of them. Remember the formula for calculating kinetic energy. We're looking at mass, we're looking at velocity. The mass of the particles, right? We're still talking about an atom or a molecule, so they're super small. But what gives them so much kinetic energy? Well, the average speed, the average velocity of a particle in air at room temperature is about 1,000 miles per hour. So we're talking extremely high velocities, even though they have a tiny mass, extremely high velocity, which is going to lead to a very high kinetic energy. Quick review about phases and phase change. I really hope that we've talked about this before. Should have talked about it in 8th grade, if not in grade school, in elementary school. So we're talking about phases, we're talking about a state of matter. And the 3 states of matter that we're going to be working with, solids, liquids, and gases. Yes, there is a 4th state of matter called plasma. No, we're not going to talk about it. If you really want to talk about it, you can go look it up, go find some information, but that's way beyond what we need to talk about in this class. So some of these words that we're going to discuss in the next couple minutes, I'm hoping you've heard before, but let's make sure we check our definitions, so we check ourselves before we wreck ourselves. So if we have our 3 states of matter, here we have gas and a solid and liquid. As we go from gas to a liquid, this process here is called condensation. That's what happens in a cloud. Right before it rains, you have condensation. As we go from a liquid to a solid, this is called freezing. Think about liquid water freezing to solid water, or what we call ice. As we go from solid to gas, this one we might not have heard of before, but we've seen it. This is the process of dry ice, where dry ice goes directly from a solid to a gas. And this is called sublimation. If we go to the reverse process from gas to solid, that's called deposition. And I made these different colors here because these are probably words that we haven't heard very much. So we want to make sure we have those definitions clear in our minds moving forward. If we continue on going from solid to liquid, again, think of solid water going to liquid water. That's called melting. And the last one, as we go from liquid to gas, the science word we're going to use is called vaporization. You'll also hear me use the more common phrase, or the common word boiling. Boiling and vaporization mean the same thing. If you look at the root of this word, vaporization, we're taking it from a liquid and turning it into a vapor or a gas. But again, it means the same thing as boiling. I'm going to use those terms interchangeably, so just make sure you recognize those and understand what those mean. Again, you can check these words on Quizlet, and you should start studying already. If we go back to look at phase changes, let's talk again. We're talking about energy, specifically the kinetic energy, the energy of motion. So let's talk about endothermic and exothermic and make sure we understand the difference of those. If we look at the root or the prefix endo, endo means in or towards the middle or coming in. Exo is the opposite, going out. And if you look at therm, T-H-E-R-M, anytime you see that, we're talking about heat or energy, like a thermometer. Meter means to measure, and so a thermometer is measuring heat or measuring energy. And we'll talk more about thermometers when we talk about temperature in our next video. So endothermic, if we put those together, endothermic means the energy is going in, so our substance, our particles are absorbing the energy. And exothermic is the particles are releasing energy, that energy is going out. Again, these words are on Quizlet. Make sure we know what these mean. I'm hoping it's review. I'm hoping you've heard of these before. All right, if we look at the phase changes, we need to think about how much energy, specifically how much kinetic energy these things have. Solids, low kinetic energy. Liquids have a little bit more. Gases have way more kinetic energy than a liquid. So as we go from solid, liquid to gas, we know we need to take our solids or our particles in the solid and we need to give them more energy so they can move more, they can move faster. And as we go from a liquid to a gas, we need to give them even more energy so that they can move more, they can move faster. And so where does that energy come from? How does the energy get to our particles in our solid and in our liquid? So again, we're gaining energy. So this process is endothermic. We have to absorb the energy from the outside. We have to heat our object, whatever it is, and to go from a solid to a liquid, our particles are going to be absorbing energy. Okay, and they're going to start moving faster. They're absorbing the energy around it. Think about melting solid water. You go from solid to liquid water, you have to heat it up. Okay, and if we continue with that analogy, if we think of liquid water going from liquid to a gas, again, we've got to gain energy, right? We've got to get those particles moving faster. So again, that process is going to be endothermic. So this whole thing going from solid to liquid to gas, is endothermic. Our particles are absorbing energy. We've got to gain energy. And if we even think about sublimation, going from solid to a gas, of course that's going to be endothermic. We've got to give it a whole lot of energy to go from solid to gas. If we reverse the process, these sometimes aren't as intuitive, but if we reverse the process, I mean, just think about it. As we go from gas to liquid to solid, our particles have less energy. Well, where does that energy go? It's got to go somewhere. So it gets released into the environment. Okay, it gets released into the area around it. So as we go from liquid to solid, as we go from liquid water to solid water, our particles have to release energy. Well, if you put your hand near it and it's releasing energy to your hand, it's going to feel warm. It's going to feel warm. Okay? And as we go from gas to liquid, again, it's releasing energy to go from gaseous water, water vapor, to liquid water. It's got to release that energy. Well, where does it release that energy to? Well, to the surroundings. And if you happen to be near it, you're going to feel that heat radiating from it. And it's going to feel warm. This is one reason why when you are trying to freeze ice, or you're trying to freeze water to turn it into ice, right? We're going from liquid water to solid water. If you put those ice cube trays, right, like you fill them up with water and put the ice cube trays in the fridge, you don't want to put anything on top of it that you want to stay cold. Because as that heat gets released from the particles to go from liquid to solid, it's going to go up and it's going to start to melt whatever you have above your ice cube trays. So if you use ice cube trays, make sure you put them at the very top of your freezer. Don't put anything above it because it is going to start to melt, at least a little bit. It's not going to melt your entire tub of ice cream, but it will melt it a little bit and shorten the amount of time that it's still good. All right, so let's get into the particulars of kinetic molecular theory. There are 5 main parts. The first one, as we've already talked about, all matter consists of tiny particles, and these particles are in constant random motion. They're always moving. Whether they're moving as much as in a gas or they're just vibrating like in a solid, they're always, always, always moving. And they will always move in a straight line. If they can, they'll always move in a straight line until they hit something. They're not just going to change direction randomly. They'll always move in a straight line until they hit something, whether that'll be another particle or whether the wall of a container, they're going to move until they hit something and then they bounce off. The second part of the molecular theory is that because the gas particles are so small compared to the amount of space they take up, right? Think about an atom. Most of the mass is in the nucleus, and you've got a couple of electrons around the outside, but most of the atom is empty space. When we're talking about gases, because the gas particles are so small compared to how much space they take up, most of that gas is going to be empty space. We're just going to have a few gas particles moving around large, large, large empty space. Because there's so much space, and because these particles are so far apart, what kinetic molecular theory tells us is that there's no attraction and no repulsive forces between the gas molecules. What that means is, as these things come and hit each other, they're going to bounce off, and there's going to be no attraction, there's going to be no push, because they're so far apart, they're so small, they're moving so fast, that any type of attraction or repulsion between these gas particles is going to be essentially negligible. We can just ignore it. It's so tiny that it doesn't even matter. And because of that, and you guys have seen this before, gases are compressible. We can change the volume of a gas a lot. We can take a huge balloon and we can squeeze it down, or we can take all of this gas and we can compress it into a canister, because there's so much empty space in between these gas particles, and compressing them together really has no effect on the attraction or the repulsive forces between them because they're so small and they're moving so fast. The fourth part is when these things do collide, when the particles do hit other particles, it's very, very important, at least to make the math work, that no energy is lost when these things collide. This is what we call an elastic collision. You'll deal more with that in physics, but this is what we call an elastic collision, where the two things are coming together and they're going to bounce off and no energy is lost. Why that's important to us, again, like I said, you're going to do a lot of that in physics. What's important to us is this point right here, where the total amount of kinetic energy remains constant. No energy, no kinetic energy is lost. So we're just going to assume that in any sample of gas in particular, the amount of kinetic energy is going to stay the same. That brings us to our last part where we talk about temperature. Temperature is, we're measuring, remember, we measure temperature with a thermometer. Meter means to measure, so we're measuring heat, we're measuring energy. What we're measuring with temperature is the average kinetic energy. The average kinetic energy. We're not measuring heat. That's a very common misconception. Temperature does not measure heat. We're measuring the average kinetic energy of a sample, of all the particles in that sample. So when we say that the room is at 25 degrees Celsius, what that means is the average kinetic energy of the particles of gas in our room is 25 degrees Celsius. It's the average. Now, we've got to remember what average means. Okay? We've got to remember what average means. Average means that some are really low, some are really high, but most are around this middle section. So if you have a glass of water at a certain temperature, are there going to be water molecules that are frozen, that are in a solid state? Well, yeah, there could be. Are there going to be water molecules that are evaporating? Well, yeah, there could be. We're looking at the average kinetic energy. And the closer that average gets to freezing, the more water molecules are going to freeze. The closer that average kinetic energy, the temperature gets to vaporization or boiling, the more water molecules are going to start evaporating and turning into a gas. So temperature is all about the average kinetic energy. So that is just a brief overlook of kinetic molecular theory. If you have any questions, please bring them to class tomorrow. We'll talk about it. Again, get started with Quizlet. There's a lot of vocabulary in this section, so it's very, very important that we get this, that you get the vocabulary down very quickly. Have a wonderful day. All right, everyone.